Okay, so now let's share the screen back. Okay, so for polar coordinates, if you remember, we had the main things were how do you get x and y in terms of r and theta? That's the main piece. And let me do that. So the first thing is you have x is equal to r times cosine of theta. Okay, and then y was equal to r times sine of theta. Okay, those are worth remembering. And let me give you the other one that's important to remember, and that is the R formula. And that is that R squared is equal to x squared plus y squared. Okay, those were important equations. And the reason why I like to write it as r squared equals x squared plus y squared is that's how you usually use it. Usually you see an x squared plus y squared and you say, ah, let's go to polar coordinates. Okay, but now we're in our world. None of this fictitious stuff. Okay, at least our seeable world, let's call it that. And our world is not XY coordinates. What's wrong with that?
It's two-dimensional.
Exactly, it's 2D and we don't live in 2D. So, you know, in a way, it's kind of ridiculous to even go to 2D, but you kind of do in math for, you know, everything up before last week, right? You do 2D only, but we need to do a 3D. So the first thing is you had the XYZ coordinates, and that we've talked about. And now what we want to do is we want to extend the polar coordinates to 3D. And the nice thing is it's super easy. So all you do is you say, well, I'm going to copy and paste the polar coordinates, literally.
Hey.
And now I need to say, well, I need z to be something. Oh, yeah, sorry. Yeah, I got to go over the quiz. Let me just finish this and then I'll go over the quiz. I forgot about that. We need z to be something. I was so nervous about the quiz. I went over the proctorial thing. We need z. So we need z to be something. What's the easiest thing? By the way, if you're talking with other people, please be. Okay, so we need z to be something. What is the easiest thing to let z be? If we were just totally lazy. Okay, if you let z be theta, then you only have two variables. And then you're back in 2D. You see that? Because, okay, if you let z be r, you still only have two variables and you're back in 2D. We need a third variable. Right? This is 3D, 3 dimensions. When I write it down, you'll say, oh, that was too easy. I didn't even think about it. Should I tell you? Yeah, z equals z. That's it. Okay. And that is the definition of cylindrical coordinates. Let's make that a little bigger because that's a biggie for today. So that's the definition of cylindrical coordinates. You just take polar coordinates and you just leave z to be itself. Just say z is z. Don't worry about it. We don't need to make any changes. What I want to do next is I want to go over the quiz because I forgot to mention that. Let's go over the quiz. And I purposely made the quiz pretty short because I knew that there'd be stress on the getting factorial to work. I knew that was going to be the mess. So what I'm going to do now is talk about hyperboloid of two sheets And we want an example equation, okay, not the definition, but an example equation that corresponds to each of the following. Hyperboloid of two sheets. Let's do A first. All right, so first thing, if it's a hyperboloid of two sheets, what do you know about the signs of the coefficients?
All but one of them is negative.
Okay, not all but one of them,
All of them, or
two of them are negative. Yeah, as Victor said, two are negative. Okay, so if you have two positive, one negative, that's going to be one sheet. Okay, so we want a hyperboloid of two sheets, and maybe I'll go over that in a minute. So let's do an example. So we can just make it really easy. You don't even need to get numbers in here. You just go x squared minus y squared. How about minus z squared? Okay, now it's important. Okay, what has to be on the right-hand side? There's some restrictions. What can't it be? Any ideas? Yeah, it can't be 0, and it also can't be negative. Because if it's negative, then you can multiply by -1, and you end up getting two positives and one negative on the left. So let's just, how about 1 sounds good? That's the easiest number that's a positive number that isn't 0. And there's your answer to A. Okay. By the way, there are a lot of other answers, so don't get nervous if yours wasn't exactly the same as what I wrote. But you need to have all of them have to be squared. You must have 2 of them are negative, 1 is positive, and a positive number on the right-hand side. And that makes it a hyperboloid of 2 sheets. Okay, let's look at B. We want a parabolic cylinder. Okay, so when you see the word cylinder, what does that tell you about the equation? What does that tell you about the equation when you see the word cylinder? Yeah, there's only 2 variables. So we need to make sure we omit one of the variables. And all you have to do is write a parabola in 2 variables. Doesn't matter which variables you pick any variable you want, any 2 variables you want of x, y, and z. So I don't know, how about y and z? How about y equals z squared? I need to be parabolic, so it needs to be a parabola. That's the easiest parabola I know. And there's a parabolic cylinder. Any questions on parabolic cylinder? Okay, notice it's a parabolic cylinder, and the parallel lines that make the cylinder are parallel to the x-axis. You don't have to note that, but I figured I might as well mention it. Part C, hyperbolic paraboloid. Okay, so we have a hyperbolic paraboloid. So that means we're kind of mixing a hyperbola and a parabola. So let's take a look. If you're going to mix a hyperbola and a parabola, well, a hyperbola has 2 squares and opposite signs. A parabola has 1 square and the other's not square. So that's what we just have to make sure is that you have to have 2 squares that are opposite signs and then one that's not a square. So, and there's lots of choices. So how about x squared plus y minus z squared equals 1. Okay, notice, by the way, if you look at the trace in the yz plane, you get y equals 1 plus z squared. That's a parabola. Do you see that? If you look at the trace in the xz plane, then you get x squared minus z squared is 1. That's a hyperbola. So then you got that mix of the hyperbola and the parabola, So that one works as our hyperbolic paraboloid, because we got the hyperbola and the parabola all in the same equation. Any questions at all on part C? Okay, let's look at number 2. Number 2 basically asks you to do the opposite of what we just did, and that is name these. So what's the name of each of the following? Here we have x squared over 4 plus y squared over 9 plus z squared is 1. Okay, notice they all have squares, and there's a 1 on the right-hand side, and they're all positive. So what does that make it?
An ellipsoid?
Yep, there's an ellipsoid. Because notice if you erase the z, then you get an ellipse. If you erase the y, you get an ellipse. If you erase the x, you get an ellipse. Erase meaning set equals 0. Look at the trace in the two things. There's an ellipsoid. Any questions at all on part A? Okay, how about part B? Well, what do you get if you erase, if you set z equals 0? If you look at the xy plane, what is it? Yeah, it's a hyperbola. And notice if you set x equals 0, you still get a hyperbola. And if you set y equals 0, you get an ellipse. And so you have all squares, and you have a 1 on the right-hand side. Okay, so that tells you it's a hyperboloid. Now the question is, how many sheets is this hyperboloid? Is it 1 sheet or 2 sheets? Yeah, it's 1 sheet, because notice that if y equals 0, you actually get a good old-fashioned circle. Okay, it has 1 negative here. So this is a hyperboloid of 1 sheet. Any questions on part B? Okay, part C. So now, what's different about this one compared to the other two? The main difference?
Equal to 0.
Yeah, it's equal 0. So notice when you have equal 0, everything changes. Okay. In fact, you can even think of this as z equals x squared plus 4y squared. Any questions on that? So what do you get? The hint is you've known the word since you were 3 years old. Maybe 2 years old. Yeah, it's a cone. Okay. It's a cone. And if you want, you can say it's an elliptical cone. If you said cone, I'll let it happen, but it's an elliptical cone. Okay, because again, it's an equal 0 here, which means that makes it the cone. Any questions on the quiz? This is a kind of a language quiz. We haven't had one of those. There's no like algebra to do. And by the way, have we had any calculus yet in this class?
No.
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 Oy.
Feels weird, doesn't it?
Well,
Oh,
actually, we
weird.
did with the arc link thing.
Oh, that's right. We did that first, like the second day of class or something like that. But not much calculus. I will warn you though, I think there's one more day of no calculus, and then everything we do from then on is all calculus. And especially what you don't do much of in the first 2 quarters, right? What are the 3 main words for calculus? What was the main word last quarter? Is integral. What is that? Derivative, and what's the third?
Differential?
Differential is the same as derivative, basically.
Okay.
Limit. Yeah, limit.
Oh, limits. Yeah.
So we're going to spend a lot of time on limits in this class, just not today. Okay, so today is, again, no calculus day. And I think we have one more no calculus day, if I remember right. And then it's all calculus from now on. Any questions on the quiz? And I know for some of you, the hardest part might have been dealing with this new computer system thing. Okay, so let's go ahead and talk about cylindrical coordinates. So here's something that should be obvious. Okay, and that is, if you want to look to see when do you think you're going to use cylindrical coordinates, what kind of surface do you think is going to be best described in cylindrical coordinates? The hint is the obvious answer.
A cylinder.
Yeah, a cylinder. Is that the obvious answer? Okay, and in particular, I'm going to be a little more specific. A right circular cylinder. Because remember, we have this new word cylinder that means that the trace on the XY plane could be any curve. But we're looking at your standard, classic cylinder, good old bottle, okay, or can, I guess I should say. And let me explain why. Let's suppose you have a cylinder. How about the easiest cylinder? So let's suppose you had x squared plus y squared. Oops, y squared equals, how about 4, just for fun? Okay, that's in rectangular coordinates. How can you convert that to cylindrical coordinates? The hint is it's very easy. So in cylindrical coordinates, it is
Z equals Z.
I like Victor's answer. R equals 2.
Oh.
Because x squared plus y squared is r squared. So r squared is 4. R equals 2. Okay. And that is a very easy description of something, right? Whenever you just have one letter as a number, and that's the description, that's about as easy as it gets. Do you agree? So that's one of the main reasons why cylindrical coordinates is important. By the way, in applications, what do you think the main application or one of the main applications of cylindrical coordinates is going to be? I don't know if we have anyone who is going into this field. I usually do. What do you think the main application in engineering is going to be? Any thoughts? Should I tell you? Yeah, but a specific magnetic field, if you look at electrical engineering and you look at the magnetic field along a straight wire, okay, or an electric field, either way. So if you look at the field that comes from a straight wire, that turns out to be a cylinder, okay, or cylindrical. And it is very, very easy to do in cylindrical coordinates because it goes about how far it is from the wire. And that's and you let the wire be the z-axis. And then you can just say that the magnetic field is a function of r only. And you don't have to worry about z, and you don't have to worry about x and y. It's just a single variable function. And that makes it much easier to deal with. So that's kind of the main. I'm not going to get into the applications because they're physics-wise, they're a little too advanced. But you can believe me that that's a major application, is when you're dealing with wiring. And wiring is a big deal. Okay, there are definitely a lot of fields that need wires. I think you all know that. I would guess so. Okay. In fact, one of my first real jobs was working with wires all day long. I was a electrical circuit technician at AT&T, and we had to deal with this stuff. I didn't do the engineering though. I just was just an intern. So that's a main thing for cylindrical coordinates. Any questions on cylindrical coordinates so far? Okay. It could get more interesting. And what if we had a sphere? So see if you can convert. Let's go. X squared plus y squared plus z squared equals, how about 25 to cylindrical coordinates? Let's see if we can do that. Let's see if you can do that, and you can put it in the chat box when you're done. So convert that to cylindrical coordinates. This one's messier than the cylinder example, as you might expect, because cylinders are perfect for cylindrical coordinates. But it's not too bad. So let's see if you convert x squared plus y squared plus z squared to cylindrical coordinates. Shouldn't take too long. You're close, Victor. Not quite though. I think you had the right idea, but you probably made an algebra error. Someone else? Okay, Ralph, you could do that, but you don't have to. Okay, I mean, you still have more work to do because you have to take that equation. There's a 25 in there somewhere. Victor's a little closer, but there's a little algebra error. I'm not seeing I'll do it. Maybe I'll jump into it then. Okay, well, the first thing I do is I say I see an x squared plus y squared. And when I see an x squared plus y squared, I can replace that with what? R squared. So I can write r squared plus z squared equals 25. Okay, now technically what you usually do with cylindrical coordinates is you want to solve for z. You want to write z as a function of r and theta. In this case, it'll just be r. So we can say z is equal to, and now I'm going to have to do that one. Yeah, plus or minus the square root of 25 minus r squared. That's just doing the algebra. Any questions at all on this converting? Okay, now let's do one that's a bit messier. Okay, for some reason you had trouble with this one, but when you see it, it's not that bad, is it? Okay, what if you had a plane? How about 2x minus y plus 3z equals, how about 4? And you want to convert that to cylindrical coordinates. Okay. So I want to let you know the first thing is you'd never do this, right? Never do this in like the real world because planes are much nicer in rectangular coordinates. But once in a while, you got to do what you have to do. Okay. So let's convert this to cylindrical coordinates. And there you actually have to use the formulas. X is r cosine theta. And then we need a 2 there because it was 2x. And then we have minus our sine theta, because that's what y is. And then plus just 3z. That's the nice thing. Z is really easy to convert. You don't do anything. Equals 4. And if you want to solve for z, you can. So z is equal to 1 over 3. Just taking the, let's make that a nice fraction. So it's 1/3 times, and then you just have 4 minus 2r cosine theta. And then plus r sine theta. And then end the parenthesis. So if you have a plane, are you convinced that you never want to, if you can avoid it, you never want to do this in cylindrical coordinates? Because it's just much, much worse. But if you have a cylinder, definitely use cylindrical coordinates. Any questions on these examples? Okay, what if we had something like, let's write the instructions, convert and let's insert r is equal to sine of theta let's go z sine theta to rectangular coordinates. Okay, how might you do that? Any thoughts? Any suggestions on a first step?
Divide by sine.
You could do that. I think it would be miserable, but you could do it legally. Yeah, I like this idea.
Yeah.
It's idea.
What Victor said.
Did Victor say it first? I see Sif saying it. The idea is that I have an r here. I'd much rather have an r squared. Do you see that? I also have a sine theta. And I'd much rather have an r sine theta. Do you agree? So if I multiply left and right by r, I get what I want. So I'm going to take this. And the first thing I can do is multiply left and right by r. So I get r squared. And then I get z times r times sine theta. Now what I can do is I can turn these into rectangular. R squared is x squared plus y squared. And that is equal to z times r sine theta. And what's r sine theta?
Y.
Y. And then if I want to solve for z, you just say z is equal to, we're going to have x squared plus y squared on the top. And then we'll have a y on the bottom. And there's my conversion to rectangular coordinates. Any questions at all on this? Any questions? Okay, so now what I want to do is say, well, let's look back at the original one I looked at, was a sphere. The sphere is kind of a mess in rectangular coordinates. And it's kind of a mess in cylindrical coordinates, right? So spheres are important. Spheres happen all over the place in the real world, especially in physics. Okay, so we want to be able to have spheres be nice. So in fact, what do you think the first thing people cared about that was close to being a sphere, close enough to being a sphere? That
The
they need to
Earth.
deal with? The Earth, yeah. Okay. It turns out we do things a little bit differently than the way they do the Earth, but it's not that different. If you talk about where you are right now on Earth, what do you have to tell people?
Your latitude and longitude.
Yeah, actually 3 things. Your latitude, your longitude, don't forget where we live.
Altitude.
Yeah, your elevation or altitude. So you have your latitude, your longitude, and your altitude. Does that make sense? Okay, I'm going to start with the easiest, and that is the altitude. Okay, and the altitude is the distance from the center of the Earth, okay, to where you are. Do you all agree? Okay, so that's the first one, and that's pretty easy to talk about. We don't want to call it R. Why don't we want? Why do we not want to call it R?
Because it's not a complete sphere.
No, but we're doing a new coordinate system, so we can talk about a sphere now. In other words, it doesn't have to be the Earth; it could be anything, any
We
sphere.
don't want to call it R because we use R in polar coordinates.
Exactly. You never want to use the same letter for 2 different things that happen in the same section of the book. That's for sure. Does that make sense? So R is a bad letter. R is already taken. Okay. Other letters you can't call it are X, Y, and Z. Do you all agree? That would be bad. Another one, which I know we've hardly done this quarter, but we will, is D. Like distance from the center. But what's wrong with D?
This is calculus.
Yeah. You just avoid D at all costs in any calculus class. Okay, so D is another one we want to avoid. So we're going to go to Greek. Who knows the Greek letter that's associated with the letter R?
Rho.
Exactly, rho. Yeah, so the letter we're going to use for the distance from the center or from the origin is rho. So let me write that down. Let's go to insert equation. And we're going to define. There's a rho. Looks like a P, but it's actually a Greek letter R. It's not a Greek letter P. So rho is equal to x squared. Actually, sorry, not rho, but rho squared is equal to x squared plus y squared plus z squared. Is important, so I'm going to make it bigger. Except it didn't work. That's better. Okay, so that's important. That's how we're going to define rho. Rho is going to be the distance from the center. Okay, and any time in physics where something acts like the distance from the center, and you're dealing with 3 dimensions, we're going to want to use this coordinate system. Oh, I haven't told you the name of it. This is going to be called spherical coordinates. So that's the first thing, is that we want one variable to how far you are from the center, kind of like your elevation, except your elevation is not how far you are from the center. I hope you all know that, right? What's the elevation?
How high you are from sea level?
Yeah, it's how high you are from sea level. Okay. And that's because we can get to the sea, but it's very hard to get to the center of Earth. Good luck. We've never done it, by the way. Okay, it's easier to go to the moon. Sounds weird, but it is. Okay, so But we can imagine it, at least mathematically, even if you can't physically get there. You can imagine there's a center of the earth or a center of whatever. And we can talk about rho squared equals x squared plus y squared plus c squared. Any questions on that? Okay, now we're going to need two more coordinates. I don't know if I just officially mentioned it, but if we're in 3D, you need three letters. You need three coordinates to talk about 3D. 2 is never enough, and 4 is always redundant. Is that clear? Just like if you're in the xy plane, or if you're in 2 dimensions, you need 2 variables. Okay, 2 coordinates. So you need 2 more. So now, this is one of those, I knew it was going to take a while, so I did it ahead of time, but I think I bunch of space. So now it's coming on. There we go. Okay, so now what we're going to do is we're going to talk about, and because I used Google, I couldn't use the Greek letters when I did the drawing. So sorry if it's not perfect, but I spelled it out. So now we're going to talk about what we got. The first thing is we're going to have our rho, and rho is the distance from the origin. The next thing is we can still use theta. Theta is not going to be anything different. Theta is going to be defined in the same way we defined theta before. And that is take your point, look at the shadow of that point onto the xy plane, and then look at the vector that goes from the origin to that shadow. You look at the positive x-axis, and theta is the angle between those. Okay, and that's the same as it was with cylindrical coordinates, which is just a variation of polar coordinates. Any questions on theta? Okay, so that's theta, and I want to mention something. And I mentioned it last quarter. I've mentioned it already, I think, lightly this quarter, but I want to strongly mention it because I wasn't able to convince you yet 2 days ago about it. What are the units of angles in this class? Always. In anything we do on any written
Radians.
must be radians. Okay. Degrees always correspond to what in this class?
Sure.
Temperature. Okay. That's an absolute. Okay. And some of you lost some points on the last quiz because you gave me a temperature when I wanted an angle. Got it?
Larry?
So that's an absolute. Is that angles in any written quiz or written exam must be done in radians.
Well,
Okay.
I've noticed on the homework a lot of times some of the questions ask for like degrees. Will
Mhm.
any of the tests ask for them?
Definitely not. Do you know why they're asking for degrees? Because I didn't write it and Bruce didn't write it. Okay. So unfortunately, I'm not the one. I didn't create all your homework problems. I don't know if you realize that.
No, I know, Larry.
Yeah. So if you ever see degrees that was written by me, it means temperature. Got it? Okay, so that's just a big note. I want to emphasize that because I'm talking about angles right now. So theta, we know. Theta is the same theta we've used before. Okay? But we need another, because remember, on Earth, we're talking about latitude and longitude. Now, it turns out it's a little bit different, the way we measure coordinates on Earth versus the way mathematicians use spherical coordinates. And my guess is it probably won't bother you because most of you haven't thought about it that much. The other angle, what we're going to do is we're going to measure it from the North Pole. So the North Pole meaning the positive z-axis. So you take the positive z-axis as a vector. You take the vector from the origin to the point, and you look at the angle between those two vectors, and that's our rho. Any questions on that? Okay, just a note, how does that differ from latitude? Anyone know? So maybe it does. If you don't, it may not confuse you at all. But it's good to know what latitude is also. Any thoughts? Direction of coordinates, not quite direction actually. It's the complement. So latitude on Earth, when we're talking about what is your latitude, is measured from the equator. Whereas in math, we measure it from the North Pole. So it's the complement of the angle. So if your latitude is pi over 3, then your rho is pi over 6, because that's the complement. Okay, that's on the North Pole problem. South Pole's a little more complicated. Any questions on that difference? It's kind of good to know for real life. It doesn't matter for this class, but for real life, it is important to realize that it's different, slightly different. Okay, so this is important, and it's really important for next quarter. So I want a lot of you are going to take it next quarter's calculus class, and that's multiple integration. And that is, what do you need rho to go from? So theta goes from 0 to 2 pi, right? So we start on the x-axis, you go all the way around, and you're back to the x-axis. What do you need rho to go from what to what? Any thoughts? This is important. Okay, so Victor says 0 to pi over 2. Okay, imagine living in South Africa. Could you describe South Africa using an angle from 0 to pi over 2?
Negative pi over 2 to pi over 2?
No, that won't work either. Still won't get to South Africa. It turns out. Negative pi over 2 to pi over 2 will be a redundancy of the northern hemisphere. You end up getting the northern hemisphere with 2 different numbers. Any thoughts? Okay, well, if you're at the North Pole, what's the farthest south you can get?
South Pole.
Exactly. What's the angle of the South Pole from the North Pole?
3 pi over 2.
No?
It's pi.
Pi. It's pi. They're on the same line, right? They're on the polar axis.
Oh, from the, okay.
Right, because we're measuring from the North Pole. Okay, from the positive z-axis. So that's really important, is that rho goes from 0 to pi. Okay, you don't need to go past pi, because if you go past pi, you could have gone less than pi and then rotate by theta equals pi, it turns out. So that will make it so that you don't have redundancies in your way of writing coordinates. So let's write that out. Write that over here. So first thing, let's do this. Actually, I can do it right here. Back. So we can say 0 is less than or equal to theta, which is less than 2 pi. Okay, you don't need 2 pi if you have 0, right? And 0 is less than or equal to rho which is less than or equal to pi. Okay, you do need 0 and you do need pi, right? Because if you don't include pi, then you don't get to the South Pole. Is that clear? Okay, but you don't have to include 2 pi for theta. Any questions at all on the bounds for the coordinates so that we get a unique system, almost unique? Okay, why is it not perfectly unique? Where do you have a problem? And the hint is very similar to polar coordinates where we had the problem. Where do you have a non-unique point? So a point that can be described in lots of ways. Just give me an example, the example. The hint is the example, there's only one.
Victor said angles.
Yeah, not angles. I think I'm looking for a point.
The origin, maybe?
Yeah, the origin. The origin. The origin has no theta. Do y'all agree? And it has no rho either. Okay, it doesn't even make sense to talk about the angle from the origin to the origin. Do you agree? So the origin is an issue, is that there's no defined angle in either angle, rho or, theta or phi, or theta or phi. Oh, you know what? I wrote this wrong. Sorry, that's not rho. I forgot to mention it is. Okay. Have you seen this letter before? This Greek letter? The one that's between 0 and pi? Okay. If you haven't, it's called phi. Pretzel. Pretzel. I like that. But it's called phi. Okay. So it's a Greek letter and it's the one they use. Any questions at all on spherical coordinates so far? Now what we need to do is we need to find out how do you understand how to go from spherical coordinates to rectangular coordinates. Okay. Okay, or even spherical to cylindrical, because we got to go all through all of those. So let me do one thing first. It's always a good idea, and that is if you talk about our rho, what's going to be the equation for rho? The hint is if you think of the equation for r, it's very similar. Any ideas? Maybe I'll even start you off. So instead of rho, I'm actually going to write rho squared. That's a hint. Yeah. So rho squared is x squared equals x squared plus y squared plus z squared. Okay, and we had that before. That was the distance formula. And the distance from the origin is that. Any questions on the rho squared formula? Okay, now we want to get what x is in terms of rho, theta, and phi. So I'm going to do that on the next line, actually. Let's look at x. And I think the easiest way of doing that is realizing that x is equal to r times cosine of theta. Okay, we had that before. The problem is r is not allowed, right? R is spherical coordinates. It's not r is rectangular, is cylindrical coordinates. It's not spherical coordinates. So what we need to do is we need to figure out what is r in terms of spherical coordinates. And that's another reason why I drew this picture. Okay, we see this triangle here. Is this a right triangle, by the way?
No.
One more guess. Yes, it is a right triangle. Because notice that this blue little line segment is vertical. And the bottom is on the XY plane. It may not look like a right triangle because we're trying to draw 3 dimensions and 2 dimensions and keep your perspective. But that angle next to the R is actually a right angle. Do you all agree? And we know that the opposite of that angle, we know that phi is this angle that's outside the triangle, but from high school geometry, if we take this top angle, that's going to be equal to phi also. Do you guys remember that from basic geometry in high school?
Yeah, alternate interior angles are congruent.
Exactly. Alternate interior angles are congruent. So that means this top angle is phi. Is that clear? And this bottom right angle is a right angle. So now I can use basic trigonometry. And what we can say now is that if we have this angle, then rho is the opposite. I'm sorry, is the hypotenuse. May not look like the longest, but it is. Everything's weird perspective-wise. So this red is the hypotenuse, okay? And that's rho, whereas r is the opposite. Is that clear? So we know that the opposite over the hypotenuse from trigonometry is what? Yeah, so the opposite of hypotenuse from trigonometry is the sine. So that means that rho, so that means the sine of phi is going to be equal to r over rho. Any questions on that? So that means that if the sine of phi is r over rho, then you can multiply both sides by rho and you get r equals rho sine phi. So let's write that down. Yeah, I'll put it over here. So r equals rho times sine of phi. Any questions on that? So now I can just substitute. So I know that, actually let's copy paste, it's less typing. So I know that r is rho sine phi. So I can write rho sine phi, then I can multiply by cosine theta. Ooh, that wasn't theta. That one's theta. So x is equal to rho sine phi cosine theta. Any questions on that? How about y? The hint is I'm just going to copy and paste and change what I need to change. There we go. So y is not equal to r cosine theta. Hopefully you know r is y sine theta. And r is rho sine phi. So you get rho sine phi sine theta. And there's our formula for y. And one of the nice things about writing it this way is I'm actually killing two birds with one stone. I'm converting polar coordinates, cylindrical coordinates to rectangular coordinates and spherical coordinates, kind of all the systems are getting converted all at once. Okay, what's the last one I need to do?
Theta?
Z. I have x and y. Yeah, z. Okay, so let's do z. Well, if you look over here, z is this blue segment, right? This blue side. Okay, so remember that what we were doing is we were looking at r, but now we don't have to look at r, we can look at the blue side. The blue side now is the adjacent of phi. So what we can say is that the adjacent divided by the hypotenuse, well, that's equal to the cosine. Okay, so it's not rho times, so that means that z is going to be rho times the cosine of phi. Okay. So we can just write that down. That's even easier. There we go. Z equals rho times the cosine of phi. And there's our big equations. Any questions on this? Any questions? So again, x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Those are kind of the big equations. Okay. I want to let you know, though, there are some applications in physics where and in particular latitude and longitude, where phi is defined as a complement, and that changes all the sines and cosines. It's kind of a pain that there's not an agreement in the world on what the phi should be. But in math, this is how we do it. So I'm doing it. Okay. Just like integrals. In integrals in some physics classes, you'll see the dx before the function instead of after the function. So it's just weird. It's just a notation issue. So I want to give you a heads up that you might see in physics a different definition of phi. Any questions on these definitions? Okay, so the first thing is, what if we had a cone? Okay, let's go. Let me do z equals insert equation. Z equals, do something simple. How about x squared plus y squared? So first thing, let's convert to cylindrical coordinates. And that's really easy. How do you convert that to cylindrical coordinates? The hint is it's really easy.
R cosine theta, y sine theta, and r sine theta.
Oh, you know what I want to do? Sorry, I didn't want a z. I want z squared. Let's do
Oh,
that.
convert x squared and y squared to r squared?
Much easier, yeah. Yeah, you could do the whole r cosine theta. You don't need to. X squared plus y squared is r squared. So if z squared is r squared, what is z?
R.
Z is r. Okay? Okay, and we'll do the top half of the cone. So we'll let r be positive. But either way, it doesn't matter. So z equals r. Isn't that easy? Cones are great for cylindrical coordinates. How about spherical coordinates? Need to go like this. Let's go to spherical coordinates. We have z squared equals x squared plus y squared. We want to convert that to spherical coordinates. What should we do? Any suggestions? If you look at it and you can make your life better, how would you make your life better? Look at the right-hand side.
Change r to
We're looking at z squared, not even r. We're looking at z squared equals x squared plus y squared. Start from the beginning. What would you like to see on the right-hand side that's not there? Okay, we'd like to see a z squared on the right-hand side. It'd be much better if it was x squared plus y squared plus z squared. Don't you agree? And there is no plus z squared. So what can we do? Suggestions? Hint is it's easy. Yeah, we add it. So if we add it to both sides, you get 2z squared is x squared plus y squared plus z squared. Isn't that much nicer? Now we can convert. And now what we can do is we can say 2. Z, remember, was what? What was the formula? Let's pull on it up in case you forgot. Was rho cosine phi. So that gives you 2 rho squared cosine squared phi. Is equal to, and what's x squared plus y squared plus z squared? The hint is it's beautiful. Yeah, that's rho squared. So we got rho squared. And now you look at that, and what can we do to both sides?
Divide rho.
You could divide by 2 rho squared, and we get cosine squared. I think I'll just copy and paste, it might be easier. Cosine squared of phi equals 1/2. But I could do even better than that. I could take a square root of both sides, and I could take an arc cosine. When is the cosine of phi equal to 1 over root 2, or root 2 over 2?
Pi over 4.
Exactly, 5 or 4. And that's like as easy as it gets for an equation. It felt like cylindrical was beautiful. Z equals R, that's kind of nice. This is even better. Phi is a constant. Okay, now you know it's going to be good. Let's see if that works. So here's what I'm going to do. So if we look at, go over here, there it is. If you look at z equals the square root of x squared plus y squared, because that's what we're looking at right now. I just took a square root of both sides. And notice what that really is just the angle from the z-axis is pi over 4. Right? Do you see the picture? Any questions on that? While we're here, by the way, I want to show you. I can go and I can add a function, rho equals, say, f of theta phi. Let me do it. Somebody does not let me do it. Just a minute. Oh, it's blocked out. Maybe I can't add it right now. Let's try refreshing because I should be able to add it. All right, well, maybe you can't today. I don't know what's wrong, but it's blanking out. But you can get, if it was working, we could get it. There's something going on here that's not working. I have to think about it. Worked earlier. But the main thing is that we know how to go from cylindrical coordinates to spherical coordinates to rectangular coordinates and back and forth, and whatever you need to do, we can make it happen. Okay, any questions at all on the different coordinate systems? Okay. In physics, by the way, when do you use spherical coordinates? Give me some examples. When we're dealing with what types of things in physics?
Rotational stuff.
Yeah, so if you're dealing with rotational stuff, especially like gravity, right? So if you're dealing with gravity, then definitely spherical coordinates are a good thing because gravity comes from a center and it expands outwards, and that's great for spherical coordinates. What else besides gravity? Potential energy sometimes, but not always. Depends on what's the potential energy of. So if you're rolling down a hill and you want to look at the potential energy, you don't use spherical coordinates, by the way. Then you use rectangular coordinates. So it's something that goes from a source is the idea. And gravity goes from a source. What else goes from a source? So there's another biggie. Idea? Okay. If you don't know,
I was thinking maybe like Kepler's laws, planetary motion.
Yeah, that's the gravity. Right, that's the Kepler's laws comes from gravity, right? Okay, yeah. Light is the other one. So if you're dealing with a light source, for example, the sun, and you want to find out, how much light is there at any point in our solar system, definitely want to use spherical coordinates because light from the sun comes out from a point source, or basically a point source, which is the sun, and it is related to how far you are away from the sun in terms of what the luminosity is. Any questions on that idea? Okay, so I think I'm going to call it. We're at time about, close enough. And let's go to